Gandhi et al. At CVM, so few papers but these methods pose it as an offline problem, which means the entire trajectory is available at the time of optimization. In this paper, we say that these ideas can be mimicked to an online setting, right? So the filtering is online with a minor latency of, let's say, 1/4 of a second. So the output is 1/4 a second delayed, but the filtering is happening, quite fast and online. So it's almost a causal setting, right? So I'll just give you another example, like what maybe. So this is a mesh flow. It's a ECCV paper. This is also for stabilization. So see, the stabilization it's much more smoother than a random thing, but you will see a lot of jerks in the trajectory if you carefully look. So you see there are a lot of jerks, minor jerks when the camera moves, and this is what a behavior which is not desired, and this is what the output of one of our algorithm called CineConvex. So it's much more stable, and especially when the actor is static, the camera is perfectly static. So basic idea is most of the other filters lead up with residual motions. Okay, so as we have been seeing today, so what cinematic literal suggests is that good panel camera is that it starts with it remains static. It does not move without unless there is enough motivation, and when it moves, it smoothly accelerates, follows the subjects, and then accelerates and again comes to rest. Right? Unmotivated camera movements are not done, and when they're done, they are smoothly done. Right? So we propose two filters. One is called CineConvex and one is called CNN. Both are online with a slight glitch, maybe a 1/4 of a half a second latency. It depends. If you increase the latency, the performance improves. Those sort of analysis I can take on questions. And both are very fast, which means the online filter, one of them, CineConvex, works at 250 FPS and CNN works at 1000 FPS. So what is the desiderata which is required for such a filter design, right? So the smoothing filter should be online and run in real time. That's a requirement. It should not require labeled supervisory data because that's very difficult to collect. So we want it unsupervised as well, and unmotivated camera movement should be avoided. For instance, when the subject frame is stationary, the camera behavior should be static to ensure a pleasant viewing experience. And it should be robust to outliers, and it should not accumulate drift. So most online filters, the problem is as they keep going, they accumulate some drift over time, and that makes them that widens the gap with the original where the date let's say if it accumulates drift, the distance between the actor and the virtual camera may increase over time. So that's a behavior you don't want, right? So mathematically, this is the formulation. So you're given some noisy trajectory x0 to xt, and let's say you want output trajectory y0 to yt in such a second that you can watch it's in a causal setting that you have the visibility to previously stabilized trajectory and the current frame, right? So the two methods we propose, CineConvex is a very simple method. It just takes the offline approach and breaks it down into a windowed approach. So it does individual optimization on small windows and propagates that over time. The details I'll talk about in a while, right? So and uses a very similar objective to the offline method. The CineConvex method uses a 1D convolution to do the same. What we observe is it's better in noisy scenarios because probably it's able to, when you're doing individual optimizations per frame, that's an individual operation. On the other hand, the CNN, since they have prediction ability, they're able to learn some data prior and do the filtering slightly better. So just for CineConvex, this is the setting. So at one point of time, we optimize the window of size t minus b to t plus f. Okay, so that's the thing, and only the part of t to t plus t to t plus p is preserved. That's the window which is actually the output is kept after the optimization, and t minus b to t is the history you are observing. Let's say the current time, and t to t plus f is the latency you can't go with. Let's say so f is usually 16 to 8 frames. We have tried 8 frames and 16 frames. That leads to violation of causality by 8 frames or 16 frames, right? So which is 1/4 second or half a second or something of that sort, right? So you do optimization per frame like this, and you use an objective function like this. So I think there are 3 to 4 terms in the objective function. One, you see that this is about that you want the optimized trajectory to be closer to the original data. the original trajectory. So here x is the original trajectory, y is the optimized one, right? And then you have a first order L1, L2, and so this is first order L1, first order L1 norm of first order, second order, and third order derivative terms, right? So this is there to give you this residual motion. This theory I'm not getting into. This is a well studied thing in offline methods. That they say that this is the way to go. And for example, the original paper which proposes is used by Google in YouTube as well as their Pixel phone. So this is well studied. So not going in details. But the problem is, if you do optimization on individual trajectories, there will be discontinuity across time. So you need to, when you do optimization over the next window, you want to make sure that some part is common from the previous window, and you put a hard constraint so that the output of that part which is common from the previous trajectory is exactly same as what you got in the previous trajectory. That hard constraint was necessary. We tried without it, and this per window optimization, if you don't put that, there is a discontinuity which you observe. And we use the state of the art Rugby solver, and we are able to obtain filtering results at a speed of 250 fps. The next idea was a CineCNN. So this is a simple 1D encoder decoder CNN, right? So we believe, or we observe, that it learns the structure better and provides improved performance, especially in high noise scenarios, and will show some quantitative and qualitative results for the same. And we also observed that if you do a bit of 1D total variation before you send it to the CNN, the performance even further improves. So the idea is you pass the original trajectory through a, so 1D total variation denoising has many forms. We use a rule based form which is very fast and more approximate. There may be better variations of it exists. So the details are there in the paper. And then what do? You take the still unsupervised, so you send the trajectory which is filtered, and then you have a loss function in the CNN which is a weighted sum of the first order, second order, and third order L1 norm. So it's very similar, but you see that you don't require a supervised data which you usually require. A loss function is working on the trajectory itself, right? So that's the idea. And the pre-processing, that how do we process data, how do we break into windows and stuff, the details are there in the paper. Again, not going to those details. Then the outputs for the quantitative evaluation, we evaluate on two datasets. There's a dataset called Baskerville dataset. This is from Disney Research. So they release this dataset where actually a robotic panning camera is following the action in the game, right? So there is another camera which observes the game, which gives feedback to this robotic camera, and it follows the game. So if you just use a crude per frame estimation, again follow, this is noisy, so they apply some filtering. So they use a Savitzy Golay filter in their paper, but we use the data and compare on that data. So basically it's a per frame estimation. Interestingly, they also apply a human operator. So there is a robotic pan tilt camera, so you know what is the pan angle of it, and there is a actual human which is also following the game, and you know what is his pan angle. So since you have the human trajectory, you can compute the quantitative losses, that how much you are deviating from humans behavior, right? So that's a very interesting thing. And then we also take some small some sequences which we call stage performance dataset. This is some clips from different stage performances, and we do a offline optimization which is considered to be quite stable and uses that as ground truth, right? And we compute two metrics. One is precision metrics, which is how much you deviate from the original trajectory, right? So human, like the ground truth is offline, or human in this case. And the second is the motion, like, so if human is static, are you static? Human is moving at a particular velocity, are you moving at a, so that's the difference between the first order derivative. We call it precision and smoothness. So these are the results on both the datasets. Baskerville dataset, we use the same training test validation split as given in the original paper, and you see that our CineCNN performs the best in terms of smoothness. Precision is roughly closer, but if you look at the trajectory, you will know that it's slightly more carefully selected. But if we try some other trajectories, we are doing better there as well. But in this particular case, we are close to precision loss, so we are almost close to other filters. If you use Savitzy, Golay, Kalman, we are using many other filters. But on the smoothness loss, there is a large improvement by at least multiple folds. And in low noise scenarios, where the noise is not so high, the Baskerville dataset is very noisy. We see that we outperform other generic filters which are not designed for cinematic, filtering by a large margin on both the matrices, right? So I'll just show the same clip I showed at the start just to show. So this is the result of optimized trajectory using the CineCN, one of the methods proposed. So you see that the stability of the camera, there are no jerks, there are no residual motions. So it's perfectly static when the lady is not moving, and it nicely follows the action, right? So on the other hand, this is a Savitzy Golay filter which is used in the original paper which proposed the basketball data set. This is what it looks like. So you see there are a lot of small jerks. Now if we carefully look, for example here, right? So there's this residual motion which causes, which is not, pleasing to watch. Maybe in interest of time I'll not show. This is a comparison with other existing methods like bilateral, Kalman, mesh flow, Savitzy Golay, and you see that the other methods are consistently having jerks and residual motion. On the other hand, CineCN and CineConvex are much more stable. So going forward, there are some qualitative results on actually the trajectory. So if this is from the basketball data set. So if you look, the blue is the human operator, the green is the unfiltered, and the red is the filtered. So if you use Savitzy Golay, you see that there are there is residual motion. So the human is almost static here, but the trajectory is moving. You see there are direction changes, there are jerks when the camera moves as well. On the other hand, CineCNN gives you reasonably static behavior, and the jerks are much lesser, and when you observe, they're actually not visible. So and these are some other comparisons with other existing filters, which are common ones. I think they can be looked at in the paper in detail, but you see that the similar behaviors is observed in other filters also, of instability and jerks, direction changes of the camera, and so on, right? Even those which actually look very smooth, for example, mesh flow is very smooth by trajectory, the jerks are less. If you look at any local trajectory, it's very smooth. You're minimizing L2 norm, also a very similar one, but you see that this residual motion problem still remains significantly there. Okay, so with this, I think I'll conclude my talk. So we propose two unsupervised filtering methods for the online filtering of noisy trajectories. One is called CineConvex, which is a per window convex optimization. One is called CineCNN, which is a 1D convolutional network which is predicting. The unsupervised nature of the proposed methods, high operational frame rates and low memory frame footprint, makes them a generic choice across a large variety of applications. Yeah, so thank you. So I think Sudhir can at least take the questions. So he's there. So any questions at this point I can answer.
Okay, I think we are short of time, but I think we take one question. Anyone has a question? Okay. Can I have a question?
Mm-hmm.
Yeah. I'm wondering if can your system handle the case that the camera is not supposed to follow the object? Say it's supposed to leave the scene, and the camera will still try to follow the object, right? And so how does your system know that it's not supposed to follow?
Yeah, so we are, in this case, we are using a detection information, for example, like we are doing a human detection, and the tracking information of that human is used to follow that, okay, this is a subject to be followed. In the other basketball data set, they have a separate camera which is looking at the entire game and tries to, based on the situation of the game, it tries to follow what is the important action. So they have a different technique to do that. So there are different ways to do it, but our paper just focuses that once you have the predictions what to follow, can you do it smoothly in online fashion. So yeah, I hope I understood the question and answered it correctly. Okay.
Yeah, that's good. Okay. There's a question on YouTube. It says that what level of training experience did a human provide in the ground truth having the camera operation?
I didn't get Sayan, can you repeat that?
Okay. Yes, the question is that what level of training or experience did the humans providing the ground truth have in camera operation?
Yeah, so now we are doing a human study. This is not part of this work, but we are doing user studies to see how humans actually, evaluate this. So right now this is more a future work if I again got the question correct. Right now we have not asked some humans to evaluate on user studies and stuff, but that is work in progress. Yeah. Okay. Thank you.
Because I think we are short of time, so probably we need to move to the next talk. Yeah. So the talk will be by you as well. Is that correct?
Yeah, yeah. I'll be giving the talk.
So go ahead. Again. Yeah. Go ahead. So we're trying to keep the time. So can you keep it in 12 minutes for the talk?
Okay. Okay.
Go ahead.
So this is the new work called. So this is an invited paper. So the paper is called Gaze Guided Cinematic Editing of Monocular Video Recording. So this is recently published at CAI 2020. Okay, so what is the problem? So here's the input video on the left. Let's say, so this is a static recording with a static camera, just looking at the entire scene all the time. And so as you see that in a static camera far away, you fail to see the emotions. You fail to follow the action, the expressions, and gets boring in a while. And this is the output of our algorithm. I hope the sound is there. Oops, what happened?
On the bass guitar, Will McGregor.
Okay, so the idea is you take this single static recording and convert into something which is able to convey the emotions much better and so on, right? So, and this is related to this problem of retargeting, but retargeting, what it does is it only solves for a X every time. On the other hand, we are simulating cameras, multiple of them, and we are doing a camera selection. So it's not a retargeting, but we would call rather a camera selection problem, right? So what is the basic idea? I'll be fast, right? So you first generate shots, you somehow estimate the importance of each shot, and then you do shot selection, and we get into the details of each of the size. So we use this previous work by Gandhi et al. To simulate cameras. So here is an example, like from a given frame, you can you can simulate large number of cameras by moving a cropping window inside it, right? So once given the camera, so this is an example of simulated cameras. Different windows show different cameras. I hope the sound is there, otherwise it will not make a lot of sense. So and then the idea is we are using the viewer gaze to actually decide where to cut. So this is the gaze thing.
Where did you hear that? I have my sources, and I also.
So once you have the gaze information, so you use this gaze to compute something called a gaze potential, right, which is based on the distribution of the gaze data. You try to see that what shot is more important, right? So you start with the lowest form of shot, which what I mean by individual actors, and you compute like based on the how far the points are and some relative measure of that to decide the weights or the importance of each of the shots, and then you use then hierarchically you build, you say that okay, for a shot containing both of them will be the gauge potential for that will be A plus B minus sum of A minus B. So that sort of formula you use to compute gauge for the upcoming later frames, right? So as you see behavior here the importance is more on this orange shot of the lady. Here, for example, it's more distributed on both, so the importance is more for the green shot, right? So which is the shot of both of them, right? And then you can go hierarchically, and build upon this. You can use the same formula, a variation of that, to really build for higher shots the potential as well, right? So, and then you do dynamic programming to okay. So you do dynamic programming to do. So ideally, you want the output to look like this. This is the output of the final algorithm itself. Okay, what happened? Oops. Okay, sorry for that. I don't know what happened. Just a second. Somehow got closed. Just a second. Okay. Where is that? Yeah. So here we go. So I hope the slides are visible. So okay, so this is the output which looks like after
Hello, ladies. Come
the
together.
dynamic
Fiona?
programming.
What are you doing here? Can't you tell we're trying to have a conversation? Well, I heard you have a little crush on Davis. What? Where did you hear that? I have my sources. And I also
So this is the idea, but before doing that, you need to solve for some other issues. For example, if you just follow gaze, you lead to frequent transitions. For example, here you see that the red is the selected shot, and you see that it moves very aggressively because the gaze can shift from a point to another, and it can be noisy sometimes as well. You lead to the problem of jump cuts if you're not carefully handling the problem as well. So you see that there are jump cuts here. So what do? We add a short transition penalty where say that there is a cost of any form of short transition, a fixed cost. If you stay on the previous shot, there is no penalty. So this is the pairwise cost, and there is a fixed penalty when you move from a shot to another, right? So that's the first term. Then you add a overlap cost, which says that if there is overlap between two shots, the consecutive shots, there is a penalty. The formula is 0 if in cases like these, and then it moves linearly to a particular cost, and it becomes very high when the overlap is beyond a number, right? So this is after the transition and overlap cost, the same video. It's hanging a little bit, but I think the idea may be across. So you saw that previously it was having jump cuts, now it just hangs. So I'll move ahead, that's fine. Okay, so and then we add another cost called rhythm, which a user can define an ideal cost. So this is inspired from previous works. This is mentioned in the paper from Galvan et al. So but the formulation is slightly different. So you add the rhythm, which says that okay, if user wants to say that okay, I want ideally a cut every 4 seconds or cut every 7 seconds and so on. So you add, instead of adding a single number, we add a range that what is the minimum cut you want. Like, so you don't cut before 2 seconds or 1.5 seconds, and you ideally should cut after m seconds. So L is the minimum shot duration, m is the ideally desired maximum shot duration, and then it automatically decides around these numbers what is the best point to cut. So then you can have different rhythms. So these are two examples of the edited algorithm with different rhythms. Okay. So you see that the fast rhythm is putting few more cuts here and there. It's still not aggressive, but I think 3-4 more cuts than the slow rhythm one. So okay, in interest of time, I'll move ahead. So we further evaluated gaze on a user study. So we designed some baselines. One is called a greedy gaze, a wide recording like the original recording. Then there's a speaker based and the random baselines, right? So speaker based baseline, for example, so a greedy gaze baseline, for example, greedily cuts to the shot which is more likely every moment, right? So here is an example of greedy gaze, but it can lead to sharp cuts, unmotivated cuts. Sometimes the noise in the gaze can lead to, also faster cuts. Sometimes there is a speaker based editing baseline which cuts to the person who is speaking all the time, right? So this is an example of that.
Desperately sick. Oh, don't you know it even yet? My arm has gotten tired of whipping you for 23 years.
So the idea is, you cut to whoever is speaking. So there is a random baseline, a speaker baseline, a greedy gaze baseline, and the white baseline, which is the original recording. And then we do a user study, and each user were asked to rate the video between, 0 to 5 on these 5 aspects, or -5 to 5. I forgot, so that is. It is -5 to 5. -5 is very bad, 5 is good. So narrative effectiveness, how effectively did the edited video convey the original narrative? Scene actions, how well did the edited video capture actor movements and actions, actor emotions, and viewing experience, like how was the overall viewing experience. And these are the results of the user study. The thorough analysis is given in the paper. You see that the gaze algorithm, which is the last one, outperforms all the baselines in all the factors. Particular baselines, for example, a speaker baseline is reasonably good for capturing actor emotions, but for actions it is very bad. As you saw, if in a music concert video, if you are introducing someone, what happens is the person may not be speaking and you'll miss it. And similar inferences, a lot of inferences are drawn and analyzed in the paper. I encourage everyone to look at that, right? So that's where I finished the talk. Thank you. Any questions I can take? Yeah.
Okay. Any questions in the audience? Let me check. 1 second. Can I have a question first? I'm wondering what kind of background does the subject you have invited to participate in the experiment have? What kind of background? Or have you invited a more experienced editor to participate?
Yeah, so they were not really experts or cinema people. They were usual people who watch movies and stuff, and mostly the students from the university as well. But they were trained, they were shown just the videos, and they were told what is jump cut, and some definitions were told to them before they started, so that at least they can appreciate what is happening, a little bit. Yeah. But more details are given in the paper. Yeah. So on these aspects also. Yeah.
All right. Any other questions?
I have a question.
Yes, go ahead.
I'm sorry if it's a bad question because I missed the first few minutes of the talk, which I found really interesting, by the way. How many people were being tracked? The gaze of how many people are involved in this? Is this a single person or a group of people that you're tracking?
So the user study one is with 5 people. We try the experiment lesser or more as well. So, but the user study is with 5 people, the gaze of 5 people, which is used. Okay, but it gives decent results with 2 or 3 people also, that there are some qualitative experiments done for that. Yeah. So
and when you did it with more than one person, was this done while the people were watching simultaneously in real time? You were collecting from everybody, or you just people watched it one by one?
One by one, yeah. So that was, we only had a single eye tracker. So, we asked people to watch one by one, yes. So it's not simultaneously, yes. Okay.
Okay, thank you.
Yeah.
Okay. Any other questions? Okay, thank you, Vinay.
Thank you.
Thanks again for the talk. Thank you.
Yeah, thank you.
So we'll move on to the next talk. The title of the paper is called Joint Attention for Automated Video Editing. is going to be a video recorded by Alan.
Yes, so there's a pre-recorded video. In this work we designed. Hello everyone, my name is Huang Wu, and it's a great pleasure to do this presentation on our paper Joint Attention for Automated Video Editing. In this work we designed a metric based on cognitive attention that we then used to implement and evaluate 3 automated editing methods for recordings of corporate meetings. This paper is accepted to ACM Interactive Media Experiences 2020 and is co-authored by myself, Trevor Santara, Michael Lees, Rolando Vargas, and Arnold Jala. We're affiliated with North Carolina State University and UC Santa Cruz in the USA and Université Côte d'Azur INRIA in France. So here's the idea. When a number of people are occupying the same space, their attention is drawn to the salient focal points within the space. These can be objects or other people. This attention is expressed, for example, through head and body motions. People will look at what others are looking at. Audio is another indice. When a person or object emits a sound, people will be drawn to and look at the source of the sound. With the development of smart meeting technologies, our capability to record meetings and gatherings is greatly augmented with opportunities towards virtual conferencing, for example. This brings in challenges of digital curation. Taking the example of the AMI database, it features over 100 hours of recordings in smart meeting rooms with 7 cameras, 3 overhead cameras in the center, left and right, and 4 close-up cameras on each participant, plus individual headsets. From all this audiovisual data, how can we create an edit for someone who did not participate in this meeting, showing at each moment the most interesting event? So using the idea of joint attention, we want to create an edit that shows the most salient point in the room at any given time. So to this end, we propose and implement 3 editing techniques based on joint attention: the audio-based edit, rule-based, and long short-term memory neural network-based edits. There's a wide expanse of literature concerning automated editing, so here I will just touch on those that incorporate models of indices of human attention. So in terms of interactive systems, human attention or joint attention has already been used for smart camera switching and for introducing cuts into 360 videos. For example, on social cameras, cameras on mobile devices use the camera orientation to determine the focus of the person operating the camera. In 360 videos, the user's head motion is used to introduce cuts towards the next point of interest. In all of these works, though, a big challenge remains, however, in identifying the joint attention from the content and the people within the videos, and not necessarily the person operating the camera or the viewer. Video summarization is another relevant field that uses attentional cues with the goal to extract a storyboard or a sequence of still frames that represent the entire video. So notably, long short-term memory networks have been used because of their ability to model long-term dependencies across a period of time. However, the goal of video summarization is not really to produce an edit from multiple camera streams, but just to select still frames that are representative of the video content. Finally, there's a lot of work on automated editing systems for virtual environments, so notably placing and selecting cameras in the 3D environment that fulfill discourse goals, and also ensure the spatial and temporal continuity of motions and actions, and apply common patterns of editing from filmmaking to achieve story or emotional goals. So 3D camera planning varies greatly from our current challenge in 2 main ways. First of all, the cameras can be positioned anywhere inside a virtual scene, but in smart meeting spaces in real life, they are fixed in a certain position. And second of all, the absolute positions of the cameras, characters, and objects in a virtual environment are known directly and completely accurate, whereas in real life, they can only be estimated. The attentional features we use in our 3 automated editing methods are audio and pose. Audio is pretty straightforward. It's the individual amplitude of the headsets for each participant. For pose, we take inspiration from automatic pose analysis software OpenPose in order to extract the facial landmarks of the participants inside the videos. And using the visibility of the landmarks on the face, the 2 eyes, nose, and 2 ears, we can approximately estimate the orientation of the head and use that, given the configuration of the room, use that to determine where the participant is looking within this environment. So to obtain the ground truth, we asked a human expert to edit 3 videos based on the definition of joint attention. That is, what is the focal point of the room at any given time. So here's an example of the human expert edit.
Well, my opinion, I think it's better under the flip, because whenever you want to the talk, okay, so then you can speak, then you can close it. Because if you put it on the flip, okay, then technical, I don't think it's feasible. Because most of the time you speak, then it will be recognized.
But if you've already got the remote control in your hand and need to open the flip to use the voice, why use the voice? Why not just use your hand? I mean, the whole point of the voice is that if the remote control is sitting there and I'm too lazy to reach over and pick it up.
So the first approach that we implemented is the audio-based edit. It is a naive approach that chooses the camera stream showing the person who has the highest microphone amplitude on their headset. And so there is no smoothing, that is, minimum shot length is 1 second, and contains only close-up shots of the participants. Here's an example of the audio-based edit.
My opinion, I think it's better under the flip, because whenever you want to the talk, okay, so then you can speak, then you can close it. Because if you put it on the flip, okay, then technical, I don't think it's feasible. Because most of the time you speak, then it will be recognized.
But if you've already got the remote control in your hand and need to open the flip to use the voice, why use the voice? Why not just use your hand? I mean, the whole point of the voice is that if the remote control is sitting there and I'm too lazy to reach over and pick it up.
The second method that we implemented is the rule-based edit. Using the extracted pose, we determine the focal point of the room and give a score to each object and participant in the room. Then the camera stream showing the object or participants with the highest score is chosen. There is a smoothing of an average shot of 6 to 7 seconds, and in the rule-based edit there are parameters to adjust, such as the weight on the pacing and the importance of the pose direction. So here's an example of the rule-based edit.
Opinion, I think it's better under the flip, because whenever you want to the talk, okay, so then you can speak, then you can close it. Because if you put it on the flip, okay, then technical, I don't think it's feasible. Because most of the time you speak, then it will be recognized.
But if you've already got the remote control in your hand and need to open the flip to use the voice, why use the voice? Why not just use your hand? I mean, the whole point of the voice is that if the remote control is sitting there and I'm too lazy to reach over and pick it up, I can just use my voice.
The final approach we implemented is a long short-term memory neural network. We take as input both the preceding and current audio and pose data, and train the neural network to output the score of the joint attention of each item or participant in the room. And so the intuition for the LSTM is that it can model long-term decisions across multiple frames. There is no smoothing involved here, so the minimum shot length is 1 second, and the neural network was trained on 2 expert edits at any time and tested on 1 and cross-validated 3 times. So here's an example of the LSTM-based edit.
Opinion, I think it's better under the flip, because whenever you want to the talk, okay, so then you can speak, then you can close it. Because if you put it on the flip, okay, then technical, I don't think it's feasible. Because most of the time you speak, then it will be recognized.
But if you've already got the remote control in your hand and need to open the flip to use the voice, why use the voice? Why not just use your hand? I mean, the whole point of the voice is that if the remote control is sitting there and I'm too lazy to reach over and pick it up, I can just use my voice.
Okay, and now I'm supposed to...
I have one question. Will there be anything written on the buttons? like that people know, or they have to learn that from a piece of paper, which button does what?
Yes, it will have, these buttons will have the numbers, and all the rest of the buttons will have symbols.
Will have symbols
Yes,
so that,
which
that,
can be easily
that the user
recognized.
really knows, you know, and
Yes.
doesn't have to
Good
first
point,
learn it.
because we need the
Yes.
symbols, because we're going into an international
And also-
market. We can't have
yes.
anything that's language
Yeah.
dependent.
But
We evaluated the three approaches against the human edit and through user evaluations. Compared to the human edit, the audio edit was more jittery and contained only close-up cameras, while the rule-based edit was less reactive to quick exchanges between the participants. The LSTM edit had more adapted pacing and higher camera variety, and with a pre-trained model could conduct editing in real time. We then conducted a user evaluation comprised of a pre-survey to see if there was any preference between different meetings, and a second part of 9 pairwise comparisons of 2 clips selected from a pool of 36 clips, where there were 3 clips per meeting and 4 editing treatments per clip. And so the users had to choose between any 2 pairs of clips which one was easier to follow and which one was preferred. The participants were not informed that there were different editing treatments between the video pairs. So first, looking at the pre-survey on the meeting preferences, we found that it had no effect later in the pairwise comparisons on whether a video clip was found easier to follow or more preferred. In pairwise comparisons, we found that the human expert edit was still preferred above all other methods, and the rule-based edit was the least preferred of all. And LSTM outperforms audio in pairwise comparisons. Though no 2 clips in the pairwise comparison were the same meeting, we regrouped the preferences for each meeting and found that consistently throughout all meetings, the human expert edit was always the most preferable and most easiest to follow, whereas the rule-based edit was least preferred. And the LSTM-based edit and the audio-based edit closely followed the human preference for human expert edit. There were a number of limitations for this work, notably the training data of expert edits was very limited, and so we were not able to train on multiple kinds of editing styles. And also post-detection for real-time systems is a bottleneck to deploying our approaches in real time that involve post. So in the future work, we would like to evaluate on a larger scale to observe statistical significance between different editing treatments on the perception of users. And we would also like to evaluate whether different editing techniques would be more suitable or less suitable to different contexts. Thank you very much, and please contact us if you have any questions. Hello everyone, my name is Huang Wu.
Okay, let's get back to the.
My name is Huang Wu.
Okay, let's get back to the.
My name is Huang Wu.
Okay, let's get back to the.
My name is Huang Wu. Sorry. I'm sorry, had some
Okay.
feedback.
No problem. So, any questions? Any questions from the audience? I wonder what's the input for the training data? As you said, the number of training data is probably not good enough. But I wonder what's the form I can put into the training data.
So the data that we input into the LSTM is already the pre-processed video, so it's not the video frame by frame exactly. It's already, we analyzed all of the pose data, so we know the exact on-screen positions of the faces, and using the visibility of the facial landmarks, we determine what is the confidence of a certain head pose if the participant is looking to the left, in front, or to the right. And so there's the confidence of that, of each pose. And there's also the amplitude of the audio for each of the 4 microphones.
Yes. So what's the total number of sessions that you have put into for training?
So the training data is always 2 meetings. Each meeting is 30 minutes long. And so we input the data per second and use one video as the test data.
Okay. Any other questions from the audience?
So the ground truth, Helen, is the user selected one, that user edited. So
Yes.
the ground truth for the LSTM. Okay.
Yes, so the ground truth of the LSTM is the expert edit. The expert, they edited the video, and so whichever camera, whatever is shown in the camera that the expert chose is the ground truth highest joint attention for that second. However, we use a exponential decay so that the importance of an object will not drop from 1 to 0 from one frame to another.
Okay, thank you.
Okay. Probably we don't have much more time for questions. So I'd like to thank you.
Thank you.
Thank you for the great presentation. So move on to the last industrial talk. The talk will be by Adam, I guess. Right?
Yes.
Okay. The title of the paper is called Dynamic Cinematography of Real-Life Sports. Go ahead.
Can everyone see this okay?
Yes.
Okay. Thank everyone for having us. My name is Adam Mahil, and I work at Unity with my colleagues who are also on the call, Gregory Labute and Christian Burkes, and we build something called CineMachine with a related product called Cinecast. And for the last couple of years now, we've been working very actively in the world of procedural cinematography on volumetric 3D content, specifically volumetric 3D content from sports. So it's no surprise that real-time and sports are doing some very exciting things together in terms of bringing the game home with XR and seeing things on your tabletop, to supplementing broadcast CG, to in-stadium events, although we're not going to stadiums anymore, maybe not for a little while still, to broadcast tools where the show creators and the directors at the stadiums can operate things not just like the sky camera, but looking at doing more work with 3D data, which brings me to my last one, which is volumetric capture replays. So this is a video that Canon released recently. This is all volumetric data, so you can put a virtual camera anywhere. And Intel is in this space, and there's others. And a great number of football, soccer, basketball, rugby stadiums around the world are being outfitted with 3D cameras, creating volumetric data. And what's very interesting about this for us is there's been incredible efforts on making very high quality data. But what do you do with it after? How do you shoot it? How do you dynamically edit? How do you make beautiful broadcast presentation with cameras that can go anywhere, because they're obviously free from physical limitations? So we're looking at the world a little bit like this, where you have sports, and then you have volumetric capture providers, and then you have high-speed networks, Wi-Fi or 5G, and then it comes into Unity, and we render it, power it, create the user experience, the interface, procedural cinematography, all those kinds of things. So this is happening. This has been there's been a few years that stadiums have had this hardware installed. There's a new stadium, basketball stadium, that has got some very cutting edge, version 3 of all this data, all this hardware going in. So we're not specifically working on this problem. We're going to assume that it's just going to be ubiquitous and there'll be 3D data coming up from games. And this is not something for us to worry about. But we are worrying about what to do with this data. So when the data comes in, it's point cloud data. So there's no skeletons. So we're doing machine learning over top, like a pose estimation to generate skeletons. So the camera says something to look at. And the offerings are, how do we get a replay on a Jumbotron screen really quickly? And then how do we beam all this data to the device so people can see and manipulate that in 3D? So this is what we've been working on. Fortunately, I can't show you the actual data. This is a sky cam. This was one of our targets. This is, some people are calling this the greatest shot in football history ever. And it is a great shot, but if you see, it's just a single contiguous shot and the camera is above the players because it's actually a real camera. It's a set of wires. So what could we do if we were freed from the limitations of hardware and camera placement? Getting cameras on the ground, doing dynamic editing, putting it in the players' heads, all these kinds of things. And then letting users see and manipulate this data and share it with their friends on social media, and those kinds of ideas. And then when we have the machine learning doing the pose estimation, we can also do metadata embedding. So we know what's happening. This player scored a goal, this player threw a pass that was however many yards. And when we put that metadata stream combined with the volumetric data and we store that, some interesting search and query ideas come up. Like, I want to see a 2-minute play of every left-hand pass that has happened this year, or things like that. So you can send queries and get alerts when very specific things happen. And then that section or those bits of volumetric data get combined and beamed. And I'll show you something on here in a second. Sent to device. The tools for the broadcast suite, obviously, this is very an obvious use for this technology where we can empower the directors to have cameras anywhere. I imagine refereeing will be very different when you can put a camera anywhere and see what's happened, and create very cinematic content nearly live or for post-game highlights and those kinds of things. So this is a close-up shot of Canon's Rugby. It's very impressive. It's basically photoreal, and you can see, it's a single camera movement. So while the processing happens very quickly, the way that the cameras are being authored is manual, like keyframing and with controllers. And we see a world where those cameras are completely automatic, and that's what we've been working on. So what we're doing right now is we ingest the volumetric data. We do pose estimation on the skeletons so the cameras can track them. We use Unity Cinemachine for creating dynamic sequences and for the mobile app input, so you can orbit and manipulate it. And we've modified our renderer to work on mobile devices and to do this stuff that quickly. But there's a lot we're not doing. And this is why it's great for us to be in this audience with you people, because you're doing some very, very clever work in this space. And there's a lot of stuff that needs to be done. So we have a thing called the CineMachine Story Manager, and it manages like what's interesting, camera transition evaluation, shot evaluation, and it helps generate an edit dynamically based on what's happening. We want to move everything to DOTS, which is Unity's performant language. Data-oriented tech stack is what it stands for, and it lets us have literally tens of thousands of active virtual cameras being evaluated. And then, sports-specific cinematic understanding, which is a giant topic. And we've been discussing like doing ML training on actual broadcasts versus a more traditional algorithmic rules for driving cameras based on what's happening. Like there's a breakaway, so we'd like to treat that a certain way, or it's a corner kick or any of the other main, game events. How do we have the cameras react appropriately? And our very lofty goal is to be the first to power 3D sports replay in a standard broadcast. So I hope we can get to that next year. So this is a question that I'd like to ask this audience. What is the best way to move forward with all these nuts and bolts? So we're going to show you where we are right now, and then you can see where we're going. So I just turned off my screen. Can you see my iPad? Is that showing okay? Can I get a confirm that this is working? Yeah, okay, great. So we've built an iPad app, and I need to apologize in that I can't show you the volumetric data specifically because we're under NDA with the sports franchises that we're using this with. So we're gonna go right up to the glass, and I'm gonna get as close as I can, but I can't show you everything. So we're calling this Unity Sports. It's running on an iPad. We've got different games, different events. And these are captured volumetric events, seamlessly integrated with broadcast, meaning we watch the broadcast, and when a replay happens, it gets turned into point cloud data. It gets streamed to your device. It gets played on here, and you can scrub time. You can pick different cameras. You can orbit. You can even tap on a player and get their Instagram page and see merchandising and what shoes they're wearing. And it's this whole ecosystem that's running on here, and it works. We have that as a proof of concept, and it's using quite primitive dynamic cinematography, and that is just Cinemachine and Cinecast tech. But we're working on moving that to the story manager and making that more adaptive. So sorry I can't show you any closer on that, but that's working here. But what I can show you is this working in a game event. Sorry, I just hit play on that. So I'm going to show my screen one more time. So this shares a lot of stuff with video games. Obviously, the camera system at some level doesn't really care if it's a soccer player or a video game. Obviously, the contexts are different and what they're doing is different. But, we still need to pick good cameras. We still need to do good edits, and we still need to provide some aspect of user control.
We can't see your screen.
Oh, you can't see my
Share
screen?
your screen. Yeah,
I'm sorry.
it's okay.
I'm jumping back and forth, and I'm going to do a live demo now, which is yet another jump. So we came from here. So this is some of the work that we've been doing with this technology in video games, and our goal is to release a suite of these controls that anyone can put into their game, and with hopefully a very minimal amount of wiring it up and connecting it. We introduce the idea of procedural cameras, dynamic editing, user control of the cameras, and to create this spectating view for games. And I mean, I'm sure many of you know how large esports are now, and they're just getting it's getting larger every day. The ability to watch games is this huge market. It's very popular, but imagine watching with agency. I'm not just watching my favorite player. I can switch between different players, or I can maybe even pick the lenses. I can say what kinds of things I would like, what the most interesting things to follow, and there's the user has some kind of agency however they view the game. So I'm going to show that right now, right here. This is a live demo. I've been told to never do totally live demos because they're very error prone, but I'm going to show you right now. Can you guys, are you seeing my screen? Do you see like a...
Not yet. Again?
Not yet?
No.
Okay, sorry. Do you see it
Yep.
now?
Yep.
So this is an internal game that Unity's made that we've put all this technology into. The first version of it, there's still obviously a lot of work to do. So I'm going to join a match, and I'm going to wish to spectate this. So these are all games that have happened historically or perhaps even live. There's no live games happening right now. So we're going to watch a historical game. This one looks interesting. It's got 8 players. It happened at this date. And I'm going to hit watch. So while that loads up, what we're doing is we're getting a stream of all this game data. And we start at the beginning of the match. So here's one of the players, and they're running around. And I can say I'm going to follow them. And I've got basic orbit controls, and I can follow them, and this is them playing the video game. Now, I can also hit a world, hit the world camera here. And what we're doing is we're switching between cameras in the world that have the best shot of this player. Now, you can see sometimes the player actually gets a little bit occluded, and that's because we're in a pre-dots version of this. So our shot evaluation is a round robin method. We've got about 125 cameras in this environment. So their shot evaluation has a slight latency to it, which is why you get these occasional shots. But there's no one touching anything right here, where it's completely dynamic editing, and we're just going between what camera has the best shot of the player. And I can pick different players, so I can actually click this right here, and we will see this next player, which is hiding somewhere, which we're not getting any good shots of right now. I'll go back to the first guy. And as more players join the game, here's another player joining. I can click on that, and I will see that player play. Now, this is a very basic setup that we have here. This is just doing shot evaluation, and it's just doing a dynamic edit to the camera that has got the best cut with some very basic rules. This project has now moved all over to DOTS, which is the faster programming language. So we're going to be able to put tens of thousands of cameras in here. And then we will add some of the technology that we worked with Mark and Quentin on for the original Cinecast, which is understanding the rules of cinematography, not cutting across the director line, not doing same cuts, some basic but very powerful and very, the difference that it makes is quite staggering once you have tens of thousands of cameras to evaluate, and then the ability to dynamically edit between them. And what this creates for the gamer is that I am now, casting this game. I can share this video, and I can speak over top of this, and this is now my cast of the game that's happening. And the audience can either watch the game live, or they can subscribe to other people casting. So we create this entire casting ecosystem. So you can see it's all right. We get a lot of not that great shots. We've got some bad editing. It's not amazing. But once we, put in thousands more cameras to evaluate from and do the dynamic editing, we'll get to the point where I think this is going to be ready for prime time. So we hope to be releasing this technology this year. So I will go back to here. Yeah, you can see, look at this. Look how much work we have to do still. There's still quite a few bad edits, and there's a lot to be done, but it's up and it's running. Okay, I'll turn that off. So let me come back to my last slide here.
Oh, I think we lost Adam. Okay, we'll have to wait a bit until he can connect again. Yeah, while we are waiting, please think of any questions you may have. Yeah, you're back.
I just clicked
Yes.
up. Too many tabs open. My mistake. So I'm going to go back to this slide and we can chat and go to questions. So yeah, that's a summary of where we are and what's going on next. And if anyone has any questions, I mean, we'd love to hear them. It would be great to hear if you have any thoughts on this space, because we would really like to. I mean, potentially, Gregory, this is what I'd like to ask you, if you can share a little bit more information around the story manager and what our goals are for this.
Sure, I can say a couple of words. Right now, what we've done, if the problem is, let's present a cinematic experience that tells the story that needs to be told. What we've done is we've divided the problem into two pieces. So one piece is what we call the story manager, and its job is to accumulate objects, visible objects of interest, and rank their importance. So the question it answers is, what needs to be seen on the screen right now in order to best advance this story? So if I've got 20 players of a game, depending on what they're doing, they're going to get different levels of interest, right? If they're just sitting around doing nothing, they're going to be relatively boring. If they're actively engaged in killing an opponent, they're going to be very interesting indeed. If they're just walking around, they might not be so interesting. So the approach is we rely on markup from the game developer to say, hey, they're doing something, they're firing their gun, or they're exploring, whatever. And the idea is the story manager accumulates in buckets levels of interest along different axes. So one bucket representing an axis. And if I fire my gun, for instance, we're going to say, oh, that was interesting. Drop something in this bucket, fill it up a little bit with interest. And each bucket has an evaporation rate. You can imagine that the interest decays with time. So if I fire a gun now, it's very interesting, but in a minute, it's not going to be very interesting at all. So that interest level just decays. So if you think about the story manager, it's just a way of accumulating for each object of interest in the game. How interesting is it? That's its whole job. What do we need to see? And the second part of the job is the cinematographer. And the cinematographer takes the output of the story manager, which is, all right, I'm going to rank everything of interest in the game according to interest. And the cinematographer tries to present this in the best way it can. So that's going to be a function of what cameras are available, what the cameras can see, what's occluded, what's not occluded. So it's going to say, all right, I'm going to take the things that the story manager is telling me need to be seen, and I'm going to try and show them somehow. And the cinematographer takes this information, and it has a bunch of cinematographic rules about what makes a good shot, what makes a bad shot, how well can we see the things that are of interest, what makes a good transition from one shot to another shot. So it's doing all of the cinematographic stuff, assuming that the information coming out of the story manager is correct. So for us right now, the big problem is in the story manager, how do we help the game developer mark up their game to say what's interesting right now? This currently is a very loose collection of levels of interest, of decay rates, of scores that all get somehow averaged out. And it's very difficult to tune this in a good way. And one of the questions we have is, would it be possible somehow using machine learning to train a good model of interest levels for a given game? That's a question that we have that we would love to try and explore. Right now, it's a manual process, and it's very difficult to tune the game, and we're not happy about that side of it. Another question we're having in the domain of sports is, well, here we don't have any kind of metadata beyond perhaps the limited stuff we can get out of poses. I know there are companies that are working on machine learning solutions to, specifically in the sports context, to try and deduce what the players are doing and have more domain-specific metadata. That would be super interesting. Another question I have right now is, well, is there a way, just by looking at the players running around, to discern some kind of structure in their movement? So are they moving in a random way, or are they moving in a more structured way? And is it possible that the more structured things are somehow interesting? I'm wondering if, in the absence of any domain-specific knowledge, that would be a useful avenue of study. So if you're looking, for instance, at an ant colony and you don't know anything about ants, and you've got 1,000 ants milling around, what are we going to tend to look at? My intuition is that somehow our brains are going to discern things with structure and find that kind of motion more interesting. And this is just an open question I'm throwing out there. Is this an interesting thing to look at? And how would we start? Okay, that's what I have to say about Story Manager.
That's great. Thanks for bringing out the questions. There's a question in the audience saying that how is the placement of so many cameras decided? Ethan?
So how's the placement decided? So they vary for each sport, but currently what we're doing is we are handcrafting different layers of camera that have got some restrictions around their performance, but they're dynamically responding to what's happening. So for example, in soccer, we have a sideline camera, and it's a dolly track. And it's a camera that glides up and down the sideline, and it follows a target group, and the target group gets dynamically populated based on things like the ball, and it's typically the ball and a couple of players that are close to it, so it'll dynamically follow where the action's going. We also have a target group for what it's composing on, and it's very often the ball and a couple of players close to it, but that does change. And there's multiple different types of this. So we've got cameras which are following each player, cameras which are on the court on dolly tracks. And what we're doing is we're blending between them based on game events. And right now we're manually doing that. But that's one of the things that we want to automate through other ML or through a real quick example of that. We might go with an overhead dolly track. As soon as we're 3 seconds from a goal being scored, we want to blend to a camera that's dynamically following the target group. That's the player who has the ball, and say the goalie. So the camera swoops right in and has this beautiful overhead shot of the player and the goal and the goal that's about to be scored.
Adam, I dropped out of internet for a couple of minutes there, so I don't know if you mentioned this, but how do we know that a goal is going to be scored in 3 seconds?
Well, that's it. I mean, and we're manually marking that up right now. But that's all of this stuff that we'd like to automate, of course. And even with some very basic game states, we can do some relatively eloquent things with the camera. But right now, we have very little access to that information. We need to generate it, and we need to work with the people who are doing the volumetric data so they can generate it. I mean, Unity is not going to be the machine learning system to create the metadata for all of this volumetric sports content in the world. At some point, we'd like other people to do it and for us just to access that.
Okay. Anyone want to respond to Greg's question earlier?
Yeah, Mark, I'd be happy.
Yes.
Yeah, I'd be happy to give a shot. Yeah, so obviously the largest issue with a game sports event is that you've got no database of existing motions and trajectories that would work well. So there's no way you could sort of train what is going to be great camera motions. But then maybe you can work with experts like shooting or editing experts and look at the problems of reinforcement learning, because with reinforcement you don't need so many examples. So it could try to derive from the data you have some specific situations and try to learn on an example basis of what's happening in those situations. And maybe also looking at gaze tracking. If you show the sequences to people and gather the gaze tracking information, you could probably try to get some ideas of what people are looking at and therefore what is important in the scene.
Well, yeah, this app. Sorry, go ahead, Adam.
No, go ahead.
This app, I see it as a wonderful way to collect data about what people find interesting and what kind of shots they like. Because what are they looking at? We should totally be collecting this data in order to train our automated system.
Yeah, the gaze stuff seems very interesting. One thing, Mark, that we've been thinking about, and I don't know, we feel like this is a good way forward, but there's not a lot to learn from the cameras from current broadcast, because the cameras are limited to, obviously they can't go onto the field and get in the way of the players. So when we speak to experts, and we have had a few conversations there, there's not a lot to learn from what's already happened, because we don't want to do what's already happened. Because if we're just going to shoot it like a broadcast, well, why don't we just use a broadcast camera? I know that's not exactly the point you're making, but what we're thinking of is this interim space where, when we know the game states, those states can drive camera behaviors, and they can help us iterate and figure out what this new camera space wants to be, because there's a lot of experimentation. And sometimes these cameras that we've never thought of before are actually great or terrible. But we need this sort of interim way to drive them that's not really going to come from broadcast, because we want to free ourselves from those cameras. We actually want to reinvent the cinematography of these sports, and we don't know what that is.
No, indeed, that's the key challenge.
Yeah. I think we have 10 minutes, less than 10 minutes left for the whole workshop, or only for the session?
I think it's for the whole workshop.
For the whole workshop.
Yeah.
So probably it's the time to close the session now. So I would like to thank all the speakers, especially the exciting work at Unity. We are looking forward to the exciting software that you're producing, and hopefully we can see it very quickly.
Thank you.
So I would like to thank all the authors, all the presenters today, and we'll close this session. And this session actually is also the last session. We don't have another room for the closing. Is that right?
Yes, indeed.
Okay. Anything, Vinette, what you want to say?
You can start, Sayan. I can add up a little bit. You can start with the closing.
Okay.
Yeah.
Okay. I think this is the most interesting experience for me. Even though it's a virtual conference, I think I pay attention to all the talks today, and it's very exciting and very tiring actually. But anyway, I think I've learned a lot, and I'm excited to know that a lot of excellent work still going on cinematography and editing, and I hope that Wiki can still go on for the next year, and hope to see you next year in person. Okay, go ahead.
Thank you, Sayan. Yeah, so certainly interesting. I think gives us time to look at each other's work, and really, I also enjoyed these things. And I should really say there's been a lot of hard work with some people at the back end, especially Helen. I should really say she has really put up an effort because things really changed. So Mark and Helen, I'm really thankful. Some point we are not even sure this will happen and so on, and I think we did. I'm happy. I think we did a fair job. Really, really great work from, and the reviewers. Everyone sort of supported, did things in time. So even after sudden decisions, we could manage. And I think we had good audience, good discussion, and hopefully we'll convert this into collaborations. And further, some of us are already doing that, but I think we can take it forward, and I think it'll be very interesting. So thank you, everyone, and we'll hopefully see you next year in person. Okay.
Well, Mark and Helen want to say something?
Well, it's very exciting event, and I'm really happy that everyone is here. All of these wonderful presentations, the great talks and discussions and questions, and it was really exciting, and I had a lot of fun. And I hope to see you all next year too.
Mark, would like to add something?
Yeah, same here, and I really appreciated the fact that everything was virtual and we had so many attendees. I mean, it's a great way to actually connect to people that can't move to events. So probably we should think in the next years of live streaming all our presentations, and that would add some organization issues. And here Helen has been doing most of the work, so we should thank her for that. Thanks, Helen. But definitely, yeah, it's a very nice way of sharing ideas in a broader scope.
Okay.
So thanks, everyone.
Thank you, everyone. Yeah.
Thank you all, and take care. See you next year.
See you. Bye.
Cheers. Bye.
Bye.